Lax Equivalence Theorem, and I will just give a brief introduction to Professor Sarvesh Kumar for our participants. Professor Sarvesh Kumar is presently designated as a professor of mathematics at Indian Institute of Space Science and Technology, IIST, Thiruvananthapuram, Kerala. Professor Kumar completed mathematics from IIT Bombay, and the research work include numerical analysis of partial differential equation and applied mathematics. As a part of the research collaboration of Professor Kumar, he has visited many universities and abroad, including University in Oxford, United Kingdom, the University of Concepcion, Chile, and the University of Bio, Chile, etc. Professor Kumar is a reviewer of many international journals and of American Mathematics Society. Professor Sarvesh Kumar has undertaken and also worked on different projects from various funding agencies like Department of Science and Technology, DST, London Mathematical Society, Indian Space Research Organization, and many others. Professor Kumar has published several research articles in journals of repute, and he has guided many PhD students for their PhD thesis work. So, with this brief introduction to Professor Kumar, may I request Professor Kumar to please start his lecture. Professor Kumar has already shared his screen. So, over to you, Professor Kumar. Thank you.
I'm good. Okay. Thank you so much for the nice introduction and the invitation. So can I start now?
Yeah. Yes, Professor Kumar, you can start.
Sure. I hope, can you see my slides?
Yes, your slides are visible.
Okay, thank you so much. So basically the task was given to me to speak on Lax Equivalence Theorem. So I mean, this is a very famous theorem in numerical analysis and one of the fundamental theorem of numerical analysis. So I hope many of you might have heard about it. So in between, if you have a question, I don't know whether you will ask directly of the chat box what we are doing here.
Sir, here, if there is any question from the audience, they can write in the chat inbox.
Okay, but I can't see the chat box become the full screen. Okay.
Yeah, but in the we have our team here. If there will be any question from the participants, they will interrupt you and they can read out.
No, that sounds good. That sounds good. So I mean, I also request you, if you have any question, please interpret between any question. If you have, then I will try to answer. Okay.
Yes.
So as I said, you might have heard about this Lax Equivalence Theorem. So let me start with why actually we need the Lax Theorem. What is this application, real application, and how do we see the application in real life also? So basically, we have to deal with the partial differential equation or differential equation, but sometimes finding their exact solution is almost impossible. We may have an infinite series solution for many of the problems, but finding a closed form solution is always difficult, and we have to look for some numerical solution. But once we just look for numerical solution, there are several issues come in between, which sometimes we ignore. And if we ignore something, then there would be that will reflect in the numerical solution. Like we have seen many realistic examples, there's the bridge collapse, etc. That is because of the numerical techniques we apply. And basically, it's nothing but numerical simulation. How do I believe the numerical simulation? So in general, suppose I have any equation, let's say given f, which is your source function, and L could be an operator. It can be linear or non-linear. It could be a differential operator. Then our task is, given f, I want to find u such that this satisfies this. This comes, of course, with some initial and boundary condition that we'll see a little later in the lecture. So for example, let's take this L is a Laplacian operator here. So our task is, given a function f, We'll see, of course, what the smoothness required on f and u. That's a later part. So given f, I want to find u which satisfies this, where L is a Laplacian operator. So as I said, we may not have the analytical solution, and we have to look solution, numerical solution. So first problem I encounter with this, in the one, actually the solution u belongs to some infinite dimensional spaces. For example, in this case, since L is a Laplacian operator, my u has to be twice continuously differentiable. That means u belongs to C2. U belongs to C2, that it has infinite dimension. So we are not infinite dimension. So our computer, etc., cannot work in the infinite dimension. Somehow we have to cut down this to finite dimension. So all the numerical method which we proposed, we are proposing today, in the future also, in the past also, we are proposing many numerical methods. The basic idea is you have to cut down this infinite dimension to a finite dimension. Or in the language of engineers, this we have here infinite degrees of freedom. We have to cut down to finite one. That's the whole idea. So how do we do that? And everything depend on this, your numerical solution or simulation, whatever do computer simulation, depend on that space which you have chosen. So this is what I look solution in some finite dimensional space, so that discrete problem can be solved using computer. So once we do that, it actually, this will transform to an algebraic system of equations. So you have fh which is given to you. Now I want to find uh in some finite dimension, and lh is the approximation of L. So this is a problem, lh equal to fh. Now this, if you have linear equation, that is nothing but linear system of equation. If you have a non-linear, then this will treat as non-linear algebraic equation. So finally we have to deal with algebraic equations. Okay, so this can be solved by using computers. That's the idea. So while doing that, we have certain requirement on this. So first one is the consistency. Whatever scheme we design, it has to be consistent with the PD. What do you mean by that? If you just in the discrete scheme, if you replace UH by U, you should get this must satisfy. That means, or in some sense, you can say when your mass size is very small, your actually discrete scheme behave like a continuous scheme. Your discrete scheme just like a continuous scheme. Yeah. So stability is small change in data should not give drastic change in the solution. That's some vague definition. I will make very rigorous little later. So it says that suppose you are working with different machines, and if you get drastic change solution, this is not acceptable, because small change data should not give drastic change the solution. And that is very important point in the mathematical modeling also. While we do the mathematical modeling, there are some error like human error, rounding over. There are many type of error, but there's a small change. It's not drastic change. So that should not reflect our solution. Finally, the convergence. So it is expected that once you generate UH with a sequence of numerical solution for each H, that must converge to U in some norm. That also matters, right? Where n is a some norm. We'll see what norm it is. So suppose we have the convergence, then next question would be how fast it will converge. For example, suppose I take two random sequence, 1 by n and 1 by n square. So of course both converge to 0, but 1 by n square converges faster than 1 by n. Why do we need fast convergence? It has it will something related to accuracy also. It is related to accuracy and the computation time also. So suppose we have a initial value problems. Let's say mth order initial value problem. So idea is I can convert this to mth order initial value problem. So any mth order problem can be converted to a set of first order initial value problem like this. Just introduce some variable u1t equal to yt, u2 y dash t, etc. Then I can rewrite this mth order equation to a first order. And the way I'm converting, then these are equivalent. Means either we solve the system of equations or directly this, then both will have the same solution. Means If I solve this, that will be solution of mth order, or if I solve this m, then I have a solution of. But why do you prefer that? See, actually dealing with mth order is difficult, but however, dealing with first order is always easy. We will tell you why and how this will reflect to a Lax equivalence theorem. That's the whole idea we have to find out. Okay, so let's see. If you have a first order initial value problem, given f, I want to find y dy by dx equal to f could be a non-linear function. So why we prefer to have work with the initial value first order? Because this has well established theory and it is very understand and implement. Moreover, whatever idea we generated for theory as well implementation can be extended to higher order, because I told you the system of first order is equivalent to having the system of equation of n order. So if you know how to work with this, then we can solve any n order equation we can solve. So, but then the problem is, before jumping to numerics, we have to make sure that our continuous problem or the difference given to me should be well posed. Well posed in the sense that it must have a unique solution and solution should depend on the data. So that's from our basic course on differential equations. If you have f is Lipschitz continuous and is continued, the domain which is given to you is a rectangle here. So then this problem have a unique solution for x. So if you see the Picard theorem is not, it's only bounded. That will give a local solution. However, if you take this rectangle, which is nothing but a vertical strip here, then if these two can satisfy, this will give you the solution for all x. That means we can have the global solution. However, Picard theorem will only guarantee the local solution. So we have to be very careful, because we do not know at which point we want to find solution. So this problem is well posed if you have the function is continuous and Lipschitz continuous on this vertical strips. So as I said, it is difficult to have analytical solution. So one has to go with suitable numerical scheme. This word is suitable is very important in the sense we have to look for a numerical techniques which will provide you the physically relevant solutions. See, for example, if I have an equation, there are n number of schemes are available. So I can apply any one. Answer is not no. We have to look for a suitable scheme. Suitable means it should provide a physically relevant solution. So how do we proceed to find the numerical solution? So the idea is, first we have to discuss domain. Domain means where your differential equation defined. Here it's an interval. So we have to divide the whole domain or interval. So in the language of engineers, it is known as mass generation. So actually everything depends here. How do you generate the mass? Because your numerical solution would depend how do you generate the mass. So there are different type of masses are there. Those who work with finite difference method or finite method, they can understand it. Like we have Siskin MS, so many masses are there. So everything depends on how do you generate the mass. There are software to generate the mass if you go more than 2 or 3 dimensions. Yeah. Then based on this discretization, we have to discretize the given differential equations, which is actually, as I told you, this LH equal to FH. So this would be nothing but system of linear or non-linear algebraic equations, and then we need to solve. But then we have to be very careful here also. Once we are solving this system, it is a very sparse system, so it's not easy to deal with. So we have to be very careful here. That's why there is a new branch of linear algebra, numerical linear algebra is there to handle the system of algebraic equations. So if the problem is well posed, we can tackle it, but there are many problems which are not actually well posed. They are ill posed problems, and engineers come across along many ill posed problems. For example, if I have a simple second order differential equations, it's a linear, and with these two initial conditions, y0 equal to 1, y0 equal to -1. Okay, and exact solution is straightforward, e to minus t. Suppose I slightly perturbed the data. Suppose like this condition I slightly perturbed is now 1. I put 1 plus epsilon. So it's a typo here, should be minus 1 plus epsilon. And then with that condition, if I solve it, this would be my exact solution. The problem is here, however epsilon is small, when n is a natural number, it can be arbitrarily large. So this term will blow up. We can't control this. So therefore, a small change, even though epsilon tends to 0, but this term would be large. So a small change data will not give you the, sorry, it will give a drastic change in the solution. This is the ill-posed problem, even though epsilon is small. So now question is, how do we handle ill-posed problem? That's a separate branch of mathematics. How do we handle ill-posed problems? So just to note, we are preparing ourselves to see the application of Lax theorem actually. So as I said, we have discussed a domain. So here the interval, so I can fix some point x plus h is the step size. You can make it uniform, and y is the exact solution at the point x, and w is the numerical solution. Then this one. So there are two type of error will come. How well numerical scheme approximates to you have a numerical scheme, so we have to see how well it approximates your given equation. Second is how well solution of this numerical scheme, that wi approximate the solution of 2. That means this error we have to see. So actually the first one is nothing but consistency. As I told you, you have a discrete problem. When t tends to 0, it should behave like a continuous problem. Then second one is nothing but the convergence. So I will directly go with the multi-step method, because to see the real application of Lax theorem, you might have also seen this one-step method, where actually the stability and consistencies come through the Lipschitz continuous function. So suppose we have a method step method. Means what is multi-step method means? To compute wi, suppose we need wi and wi minus 1 here. Okay. So let's say here, suppose we need wi minus 2, wi minus wi to compute wi plus 1. So you need more than one step to reach somewhere. That's called multi-step method. So this is 3 step, because you need 3 steps to reach at wi plus 1. So in general, the mth step method can be written in this form. Okay. So here, this can be a scheme, and a1, a2, b0, b1 are some real numbers. So you may think that I can generate some numbers and have the scheme. Answer yes. But then, given these numbers ai, bi, we have to make sure that the scheme has to be consistent, stable, and convergence. That's it. So how do we drive this multi-step method? It's very straightforward. You integrate this from xi to xi plus 1, and this function f, you can approximate by polynomials. You can use Lagrange interval polynomial, right? Suppose this, and then you can generate the schemes. So then, as I said, we have to worry about 3 things: the consistency, stability, and the convergence. So if you apply this Taylor's expansion, then it's straightforward to see that if you want to have a local truncation error of order HP, this you might have seen the previous lecture, right? Local truncation error. So if you want that local truncation error to be HP, then this AIs and BIs must satisfy this, where M is the step size. M is the step size. So you can pick up any number AI and BJ which satisfy this. So for consistency, the P has to be 1. That means the first condition should be satisfied. So here are the examples, if you might have seen also in your course. So there are 2-step Adam-Bosworth method. That means I have chosen number A11, A20, B1, and then I can check whether it is consistent and what is the order of consistency. So this is satisfied, right? So that means these schemes are consistent with order 2. Here consistency order 2. Similarly, if you have Milne's method, then this is 4-step method. These are the A1, A2, A3 are chosen such that this would satisfy. So what about stability and consistency? For consistency, P has to be 1. That means if you choose your A and B, we satisfy these 2 equations. So I have consistency. What about the stability? I mean, without going much details, if you might have done it. So to check whether multi-step method is stable or not, we construct a polynomial lambda in lambda with this one. So these are numbers, a1, a2, am's are there. These are numbers which we already have. So now finding the roots of this. Let's say lambda is a root. If mod lambda is less than or equal to 1 for all 0 in lambda, or if lambda is 1, then lambda must be simple. It should not be repeated n number of times. Then this scheme is stable. So there's a famous theorem: a linear multi-step method is stable if and only if root condition is satisfied. Okay, so we could see the consistency and stability based on the numbers ai's and bi which we have. Then question is, what about the convergence? What about the convergence? So as we know, this mathematician Lax, I will come to Lax equivalence theorem a little later, but this is not a Lax equivalence theorem. This is known as Day-7 theorem. Okay, but actually the Lax also contributed. It's known as Day-7 equivalence theorem. So if you have a consistent multi-step method, if you have a consistent, how do we check the consistency? That is just through this one. AI, and you have the numbers A and B. If satisfy this scheme is consistent, then if you can check the stability, that will give you the convergence. Or if you are not able to check the stability, you can check the convergence, then will be also give you the stability. Means what? For consistent multi-step method, stability and convergence are actually equivalent. If you have one, another will follow. So in most of the method here, actually proving stability is easier, but then proving convergence is difficult. So then this theorem would help us if you have the stability, and then it will give the convergence. Moreover, the order of consistency error, this is what I told you. Yeah, if you have a local truncation order P, that would be our rate of convergence. That would be your rate of convergence. So if you improve the truncation error, order of truncation error, that would be reflected in the order of convergence. So that's a very big achievement, in the sense you can improve the order of convergence as you wish by choosing suitable AI and BJs, which are the which are the real numbers here. So if you see, different methods are there to handle it, right? So different method based on how do you choose these numbers A1, A2, AM, and B0, B1. That's all, nothing else. So you can generate your own scheme by choosing the suitable A1, A2, and B1, B2, provided you must have the higher rate of convergence. So this theorem by Lax and Day-7, two mathematician, that will help you. So if you have the stability, then I have the convergence. Moreover, order of local truncation error will give you the order of the convergence. So Day-7 was a Swedish mathematician, and his work particularly influenced in the theory of numerical analysis of differential equations. So just one comment here. It doesn't matter, your f could be nonlinear here. So that means this Lax Day-7 theorem is applicable for nonlinear OD also. This is applicable for nonlinear OD also. So as I said, stability is equal to convergence. Suppose one is not there, either stability or convergence, what would happen? So let us take an example where scheme is not stable. Then can we have the convergence? Of course not, as per the theorem. So suppose I take a simple example, y is equal to 4x root y, this, and I just pick some random a and b. Okay, this is my scheme. This is my scheme. I can generate for a and b the schemes, and if I compute the solution, my exact solution for this, like 0.2, 1.0, etc. But numerical solution, they is no longer close to the exact solution. So that means I do not have the convergence. I do not have the convergence. So let's take another example of stability. So suppose I take this linear, we divide that 2 minus 2y0 is 1, and it is my exact solution. This problem is well posed. if you just perturb epsilon, then of course this will converge to this. So use any midpoint rule. Suppose I use this, and then take different time step delta t1, delta t01, and then we'll see the numerical solution. Okay, this is no longer you see to the exact solution. However, this is a consistent scheme, but it doesn't have the convergence because of the stability. So if a scheme is not consistent, what about convergence? Of course, it's same. If a scheme is not consistent, we cannot expect the convergence. So for the same problem, suppose I pick this A and B in this manner and compute my solution. So if you see the numerical solution h equal to 0.1, this is my solution, right? But if I take h 0.05, what happens? Means convergence is what? If you take h tends to 0, your US should be close enough to you. Or in some sense, if you have the measurement or norm, that must tends to 0. So we see if you take h 0.05, this is no longer close. And hence we don't have the convergence because this is getting too different. Okay, now let us go with more general setting, and here we see the Lax Equivalence Theorem. So if we start with the same thing, given a y, I want to find x such that Lx equal to y. That's a problem. So here x and y are some Banach spaces, and L is a linear operator. We have to very clear. It's a linear operator. We'll see if L is non-linear, then things are very different. So L is a linear operator. Okay. So we assume that our continuous problem is well defined. That means for any y, there exists a unique solution to this, right? Or precisely what we are saying, if L is 1, 1, 1, 2, then your L inverse also has to be continuous and 1, 1, 1, 2. This is what it is. This is what we have. So since you might have forgot some definition which are important for me today at least, so I will recall some of the definition. So what is the Banach space? So if you have a normed space means you have vector space with a norm. Norm is a measurement. So you have a normed space X overall. So it's called Banach space if every Cauchy sequence in X converges with respect to the norm. So why it is so important? It will give, it's nothing but a complete normed space. A complete normed space. So if you take any Cauchy sequence, it will find its limit inside the space. It will not go out. It will not go out. So that's the basic idea. Actually, we also use in differential equations once you go numeric. So like U8, it's nothing but a sequence. For H1, H2, Hn is become a sequence, right? So when h tends to 0, this also must have the limit in the space. And continuous map means suppose x and y are two spaces. If xn converts to x, that means then f of x1 should converge to f of x in y. And bounded, since we are linear, so here bounded and continuous linear maps are same. What is bounded linear operator? Set of all linear operator from x to y, which are bounded, is set of bounded linear operators. This is what the basic thing you might have seen, but I have to recall because that's very important for today. Then you might have heard about this uniform bounded principle. So today we will see a real application of this uniform boundedness principle, which we have seen in the course of function analysis. So why it says, suppose X is a Banach space and Y is a normed space, then F is a subset of all the bounded linear functions, operator from X to Y. Then if you have this set which is bounded, then for each bounded subset of E, this is actually bounded, or that is my F is uniformly bounded. This is what the uniform bounded principle is there. So this norm is known as operator norm. This norm is an operator norm. F is an operator. This is given by this, or you can rewrite in several ways this operator norm. So it's nothing but supremum of fx in y, where x belongs to s. So there are a few more definitions for the operator norm, and they are equivalent. You can write the way you want. So once you have the definition, then it will satisfy this. This will satisfy. So see, that's precisely we are saying f is bounded. Capital F is bounded. That's why. So now let's go to our discrete problem. So let me recall the continuous problem. Given y in a Banach space y, I want to find x such that L x equal to y, where L is a bounded linear operator. In fact, the same idea you can, if you think L as a matrix also, you can work with the system of algebraic equation also. It can be, L can be any operator. So it's the most general setting. L can be any operator, it can be differential operator. It can be your matrix, but it has to be linear. We'll see why the linearity play a role here. So now I want to go with discrete scheme. So discrete problem is given y in y, find xh in x. We'll see that also. But I told you we have to cut the degrees of freedom here. This is again infinite dimension. So we'll see what difficulty we'll face there. So find xh in x such that this satisfies this. Okay, this is what it is. Where LH is some approximation of L. Now, suppose that LH also a bounded linear operator from x to y. Where this is your mass size. This is your mass size. So S is a family of discretized all. So LH means what? If you take h equal to 1 by 2, we have L half, 1 by 4. It's a sequence of L discretized. So we also assume that is well posed in the sense LH inverse is linear and bounded map. The norm LH inverse, however, could depend on the parameter h. So this may have a unique solution, but the problem would be this LH inverse will depend on the mass size h. So those who works with the numerical analysis, so if they depend of h, then it's very difficult to have the convergence. So let us define the stability the way we are defining earlier. So this is the precise definition of stability. So your scheme, the discrete scheme is stable if your LH inverse is uniformly bounded. This C should not depend on H. That's the idea. This C should not depend on the mass parameter, that is H. If you could have, then your scheme is stable. So this should be uniformly bounded. It doesn't matter on H, it should be uniformly bounded. For each H, you have to be bounded. Then consistency. What happens then? This LH should behave like L. I told you. Your discrete operator LH must behave like L. That means what? Your discrete column should behave like a continuous column. That's the idea. So LH of x and Lx in the norm-wise should tends to 0 as h tends to 0. So there are different interpretations of stability and consistency, but if you understand it, they are actually same. Concept is same. Okay. So what precisely is saying the stability is means what? If you have LH inverse, that is precisely we are saying your solution should not blow up. That means xh, it should be bounded. That's one meaning of stability. Okay. XH is bounded. XH is bounded. Okay. So, what about convergence? Convergence is nothing but we see how XH approach to X. This is your exact solution or solution of the continuous problem. XH is a solution of discrete problem. So we have to see how it approaching X when H tends to 0. So as I said, convergence means XH should converge to X in the norm X when H tends to 0. So there are many schemes which is consistent but not converse. For example, if you have dealt only with some finite difference scheme, which I pre-assume that you have done finite difference schemes. So I take this L is a linear operator, which is x partial derivative x with t and u. This is my linear operator. So if you apply this finite difference scheme, and this is my LH, this is my LH in this case, right? This you might have seen before. Then you know this is consistent. But can we have the convergence? Answer is no. If you have this grid point here, right? And if you see the approximate solution, we have seen the instability in the solution. So because of very large oscillations are here, so this is consistent, but this scheme is not convergent. So now question is like in the multi-step method, we could see a relation between consistency, stability, and the convergence. Can we have such relation here also? Because this L need not to be, sorry, let's go. This L, it need not to be only a differential, it can be a partial differential equation also. It can be a partial differential equations also. It could be a parabolic, it could be hyperbolic, it could be elliptic or whatever. So, but I want to put everything under same umbrella. I want to put everything under same umbrella. But in case of ODE, that was different, right? That was totally different. That is only for differential equations. Now we want to generalize everything and put under same umbrella. So L could be on any operator. If you go with heat problem, heat conduction equation, you have parabolic. If you have hyperbolic equations, wave equations, or you can have the elliptic equation also. So we can generalize everything under one umbrella. So now we want to see the same thing what we have seen in the multi-step method, which again insists that only for differential equations. But I want to generalize this idea for partial differential equations. So there were two mathematicians, P.D. Lax and Richmond, and you might have heard that P.D. Lax recently passed away. And actually, I would say what we do in the numerical analysis and has some application because of that actually Lax. Because it's not only Lax Richmond theorem he has given the most important theorem is Lax Milgram theorem. There are two mathematicians, Lax and Milgram. So let me go one by one. Maybe I start with last. So what does Lax Milgram lemma does actually, or theorem does? So it applies to both. You have continuous problem and you have a discrete problem. It will give you the well-posedness of these two problems. Otherwise, proving the well-posedness of giving differential partial is very difficult. So that we do with the help of Lax Milgram lemma. And it's again the more general setting. It's not one for one PDE. If you have satisfied the condition of Lax Milgram lemma, it can be applied to any PDE. It can be any PDE. Then you might have heard about Lax Windorf theorem and Lax Equivalence theorem. So Lax contributed a lot to applied mathematics, and several applications is there. Okay, and this Richmond is contributed for this Lax Equivalence theorem, which we call Lax Richmond theorem today. So Lax is a Hungarian-American mathematician, and Richmond is an American physicist and mathematician. So basically, Richmond contributions are in computer CFD and numerical methods. So these two, Lax and Richmond, have given one theorem which we actually sometimes call Lax Equivalence theorem. It's actually Lax and Richmond theorem. So what is that theorem and how it helps us, that we have to see. We will follow same philosophy what we have done with the differential equation. So what we want now, we want to move from differential equation to partial differential equations. Okay. So this is what famous Lax Equivalence theorem, or I should call this Lax Richmond equivalence theorem. So let xh and x are solution of 6 and 5. So that means what? Xh is a solution of discrete problem. It could be any. and x is the solution of your continuous problem. Suppose this is consistent, means what? When mass size tends to 0, your discrete problem behave like a continuous problem, or LH is some sense become L. Then it is the same thing. The stability will give you the convergence. Moreover, convergence give you the stability. Means actually they are same. So again I repeat, sometimes it's difficult to have the stability. Then proving the convergence is difficult. It depends which method you work. Okay. So sometimes we may see the convergence but not stability. But by Lax theorem, actually both are same. If you have one, others will follow. So let us see the proof of this theorem, and that is why I have recalled some real form function analysis to prove in different way. So this is error is this x minus xh, right? So x will satisfy your Lx equal to y, and so I can rewrite this in this fashion: LH inverse LH of xh. So using the linearity LH, we can write LH is a linear operator, right? I hope you understand linear operator. So I can rewrite this term as LH of xh. Hence, this x minus xh can be rewritten as LH inverse. You can apply individually this. So we have this Lx equal to y, and it described equation is Lx x equal to y, right? And there, hence, LH xh is nothing but Lx, right? Because this is your y, So x minus xh, if you just see this here, is nothing but LHX minus LX. So now you apply the norm on both sides in x, then this will be the norm. We have this. Now, it is straightforward to see if I have the stability, that means LH inverse is bounded. This is what let us recall the definition of stability, right? Yeah. LH inverse is bounded, or it is same saying that my xh, the numerical solution, is bounded. Yeah. And so that we can rewrite, right, by the definition of operator norm. So if the scheme is stable, that means this LH inverse is bounded, right? This is given. So now it is this equation, nothing but this will satisfy this, right? So it is given me that this is consistent. So what is my definition of consistency? Means LH will behave like L when S tends to 0. That means this term goes to 0 when S tends to 0. So therefore, since the scheme is consistent, and hence I have the convergence. Therefore, I have the convergence. So the stability will give me the convergence. So what about reverse now? If you have a convergence, can we have the stability, right? So on the other hand, suppose consistent and convergence. So convergence is what? This xh LH inverse y, right? That means what? Your LH inverse y is to converge to L inverse y. Xh converges to x. Xh converges to x means this will, when s tends to 0, this will happen. That means what? This sequence is convergent. This sequence is convergent, and that's why it's bounded. This again, the convergence sequence is bounded, and now I can apply the uniformly bounded principle. I can apply uniform bounded principle, right? So then we conclude that with this, since it is bounded, this LH inverse is also uniformly bounded, and that is actually a precise definition of the stability. If LH inverse is bounded, it's the stability. So it will give, if you have a convergence, it will give you the stability, okay, by uniformly bounded principle. So now we have a few observations here. See, Lax equivalence theorem may not be needed to use for error analysis of this, since the space xh and yh are used to apply xhy. So I don't, now I have it x, right? And the equation may not be solved exactly. So it's not possible that you have LH xh equal to Lx. No. Instead of that, what we do, we, as I told you in the first slide, so you have like we have a capital FH there, right? So we have to solve this. LH xh equal to YH. equal to, for some YH, I want to, this is actually the discrete problem is. But then, now there are issues. If you have XH space, so far we are dealing with only X, there was no XH. But the problem, if you take X in finite dimension, I have to work with the finite dimension. That's all. So this XH may not be a subset of X. So what we do with X, I may not do with the XH. So if this is the case, XH is not subspace of X, then how do we apply your Lax equivalence theorem? If XH is subspace of X, whatever we have done is perfectly all right. There is no issues. So like if you go to finite element methods, there are several versions of finite element methods. So version means it depends how do you choose this finite dimensional space. It is subspace of the bigger space or not. So like we have a non-conforming finite element or discontinuous finite element where actually the case this XH is not a subspace of X. Then how do I deal with that? Okay. So in that case, the error which you are writing here, no, XH minus X. Suppose XH come from XH, which is not a subspace of X, is actually not meaningful. Okay, this is actually not meaningful. Then instead of that, okay, we will try this XH norm instead of this X norm. But the problem is same. This X minus XH does not make sense. That's something. X minus XH does not make sense. So what to do? That's the problem. So to overcome this, we introduce two operators, IH and PIH, and then rewrite our problem in different way. So you have a YH. So I will write here in place of YH is for any Y is this YH, right? Capital YH. So PIHY. And now given problem is given Y and Y, find XH such that this satisfies this. Okay. We'll see why we are doing this. So now the discrete will be denoted by there are two operators. Here is not only one. Sorry. Earlier we have LH. Now we have PIH also operator. Now everything we have to do with the two operator. Consistency, stability, and it should come with the two operator. See, the operator IH, it has no role here. It's the intermediate operator which is used for the error analysis. And so all the numerical methods are developed based on how do you define this PIH and IH. They are not unique. They are not unique. So what do you mean here if you have two operator consistency? So we say consistency with order R if there exists an operator IH, we'll see IH such that this satisfied this equation. And convergence means this IHX minus XH should be of this R, CH. This one. So here the rate of convergence is R. That's the mean. So now suppose your LH PIH is consistent with order R. That means they must satisfy this equation, right? And the scheme is stable. Then we have the discrete scheme with convergence order R. How? It's straightforward to prove it. So you want to prove that we want to prove now this should happen. IHX minus XH should be there. Hello? Hello? Are you? Hello, are you following me?
Yes, sir, you are audible.
Okay, since there were no so here I said this IHX is the operator from X to XH. So both belongs to XH. So this makes sense. That's why we have to introduce this IHX minus XH. Now both belongs to XH and therefore this is meaningful. Okay. So now by the definition, this LH, what we have done earlier, same thing, LH inverse LH, this is same. Now you apply the linearity of LH, and from 10 we have this, right? So it's straightforward that IHX since LH was bounded, right? Just follow these steps. So you get, and this is the your constancy error. This is your constancy error, right? Which of order R. So therefore we have the convergence rate R. That's because of, again, Lax-Richmond theorem, because stability should give the convergence. So now, actually, how do you measure X and XH? So suppose you want X in X, you don't want to impose to XH, right? So idea is you can define another linear operator PH from XH to X, from XH to X. Then you see X minus PHX will make sense. But it should be such a way that should be a bounded operator in this aspect, okay? Should be bounded. Now assume that you have a consistency, which I have just introduced, and the stability. Then this approximability, if you have, then we have the convergence X minus PHXH. So now this is also in X, that's the idea. We don't want to do anything with XH now. We want to do in the space, that the Banach space is given to me X. So now I can actually measure the X minus PHXH in X itself, not in XH. And that, if you have this actually you get the same order here, H of R. So if S and R same, then you get this is convergence rate as R. If, or otherwise you have to take the minimum of these two, whichever is minimum, that will happen. Okay. So the proof is again just an application of triangular inequality. Just means you decompose the error PHX by introduce this PH IHX, and by triangularity you can just separate this, right, and apply this what is given to me, right, and we get the order of R and S directly. We get order of. But then it is not always easy to have such a linear operator which satisfies this property. That's the problem. So another idea is what we follow in finite element analysis, actually embed both X and Xn to a larger space. Our problem is XH is not a space, subspace of X, right? So the idea is you enlarge to some other space, and call that space, let's say X plus XH. Now do all the analysis in the X plus XH space. Similarly, I can do with the Y and YH. That's the idea we follow in the finite element. You just enlarge the space and then work with that. So I just repeat why this is so important. Sorry. Yeah, this happened because of XH is not a subspace of X. If XH is subspace of X, then nothing to worry. You can work with the X itself. There is not, because X minus XH will make sense. There is nothing to worry. Everything we can do with the X itself. Okay. Yeah. So let me tell you that Lax equivalence theorem is not applicable for nonlinear problem. Suppose I'll take this Burger equation or nonlinear advex equation ut plus ux equal to 0 with this initial condition, and you know this is the exact solution. So if I apply the scheme, which is actually consistent but condition is stable, you might have seen this condition is stable, right? Then this is my initial solution, right? The dot, and this is that. So it is not matching at all. Understand, here you see the difference here, right? So this then converges. So what we have done here, we have taken 200 mesh point with t is 0.5 small enough, right? So this is consistent here, is stable, but then converges. So that means what? A scheme is consistent, but stability will not give the convergence because the problem is non-linear. So there are some limitation for the Lax-Richmond theorem, or if you call Lax equivalence theorem. So Lax equivalence theorem is applicable only for linear partial differential equation. It's not applicable with non-linear PD. Another problem which we have here we require the completeness. That means you need that X should be a Banach space. Means what? That norm space has to be complete with norm. Otherwise, we can't do that theory. But there are many spaces which are not complete, and we are forced to define our PD on those spaces. Like X, no, there are many PDs which is defined, but X is not complete. So we can't apply there, even though it could be a linear PD, but I cannot apply Lax theorem to that particular PD. Another problem is if you have some similarity in the solution.
Sorry to interrupt you, sir. One query is there.
Sorry?
Yes, sir. Sir, please explain 36 slide again.
36.
Yes, sir.
Yeah. This one, right?
Yes, sir.
Yeah. So they can speak up? Or I have to see chat box, right? Or maybe I'm just going to finish, then they may ask, right? Yeah, just give me a couple of more. So what a doubt, by the way, I can take the doubt now. Sorry.
Sir, he is asking.
Your voice is breaking anyway. Sorry?
The query is discretization is not convergent.
Yes, exactly. Yeah, this is what I was trying to say for nonlinear problem.
Okay, sir.
Okay, sorry. Okay, let me. Yeah, so this is what I want to say. This Lax Equivalence Theorem is only applicable for linear PDE. Just now we have seen example, if you have nonlinear PDE, the stability will not give you the convergence, right? Another limitation is the completeness. So many PDs, we have defined the space which are actually not complete. Then we can't apply the Lax Equivalence. And if you have a singularities, then again we cannot apply. However, this Lax Equivalence Theorem is actually applied for nonlinear ODEs. Maybe just one application of find difference scheme for the Lax Equivalence Theorem. Just I'll quick finish. So suppose you have a Laplacian equation and you apply the find difference method. So straightforward is that. So by using Lax Equivalence Theorem, you can actually prove that this is a convergent with order 2. Okay, so I stop here. Thank you so much. And now if you have question, I would be ready to answer. Thank you so much.
Thank you, Professor Sarvesh Kumar, for a very nice and informative lecture. So, audience, if you have any question, you can write in the chat box.
Please, I think. Yeah, Nikhil, yes, this kind not convergence. Yes, this is what the answer is. Yes, it's not convergence. Okay. Yeah, so question is, how does regularity affect the numerical solution? So if you work with find difference method, which you have been working, right, to suppose, then you need that your solution should be smooth and having C2, right? Once you find the convergence, the you require should be C2. C2 means what? Twice continuously differential functions. If you don't have the U in C2, I can't prove the convergence there. So it depends. If you go with the finite element methods, I do not require that much smoothness. Okay.
Any other question, participants? You may write in the chat box.
Okay, so let me conclude. So we should all appreciate this Lax. He had several contributions in applied mathematics, in particular partial differential equations. And somehow, without understanding the theorem, we apply here and there. So it has no limitations, but as long as you have a linear PD and your space is complete, yes, stability will give you the convergence always. That's all from my side.
Thank you, Professor Kumar, for a very informative and very wonderful lecture. I'm sure that participant must have got the knowledge about the field which you have shared with him. And a few participants are appreciating your lecture. Also, they are writing thank you, sir, also. And may I request to